Physics chapter 19 theory video 3 this figure 19.5 this represents how the separation with separation how the potential energy increases. You need to understand that the potential energy is negative uh, when it is when the separation is less, that is when it is close by. uh, the potential energy is highly negative. Then when the separation is infinite, then it becomes zero. So at infinity, the highest potential is present. The kinetic energy is obviously due to something, the motion of something, you know that, and the equation is half mv squared. Then in this diagram in 19.5, it describes the electrical potential energy. So in here the electrical potential energy of these two atoms is described here. So the R is separation, so the gap between these two. When the separation is highest, so when the separation is at infinity, you have the highest potential. That is when you know that when the when the negative value increases, the value, the true value of it decreases. So 0 means the highest potential. Then so then work must be done to separate these atoms. You know, we discussed that in the earlier video as well. So so based on that principle, there are three things that we need to understand. The first one is the electrical potential energy of two atoms very close together is large and negative, right? The electrical potential energy of two atoms very close together is large and negative, so it has a larger value and is negative. As the separation of the atoms increases, their potential energy also increases, right? Here you have to remember electrical potential energy and potential energy identified in two different forms, okay? Then when the atoms are completely separated, their potential energy is maximum and has a value of 0. It has a, the 0 is the highest electrical potential energy. It may seem strange that the potential energy is negative, and you will see in chapter 21 why this is so. At the moment, just notice that as atoms and molecules become further apart, their potential energy becomes less negative, and so they have more potential energy. So if the value is lesser, you have to remember 0 is the highest potential. So that means if the negative value is higher, it has a lower potential energy, right? Lower potential energy. Now in section AB, the ice in the graph, you can see that in this graph, refer to this graph please. From A to B, ice is there. So you know the freezing point is 0 degrees Celsius. So when the temperature rises, the molecules would gain energy and start to vibrate faster, right? So you know this results in vibrational kinetic energy to increase, right? So that means in this period of time, there is a little change in the mean separation of the molecules. So because the molecules are not really separated by a large extent, there is only a little change in the electrical potential energy. Then from B to C, at this point, they become, that is the point when they actually start to, they change their state from B to C, right? As you can see here, this part B to C, it changes, right? the state. Then in this point, right, when it is becoming disordered, generally there is a little bit of a higher increase in the electrical potential energy. Then C to D, once again, from 0 to 100 degrees Celsius, they start moving rapidly, increasingly rapidly. That is, higher the temperature, higher is its movement. And at this point also, still, it is in water form. And as you know, water at 0 degrees Celsius and water at 2 degrees Celsius and water at 99 degrees Celsius, it is the same amount of water, right? So the separation is actually the same, right? They move, the kinetic energy is increasing, but their mean separation is still the same, right? So as a result, the electrical potential energy is also wouldn't change that much. Then from section D to E, so obviously that is the point when it is turning into a gas. Now at this point, there is a little, beyond this point, there is a little bit of a change. Water is boiling. They are becoming now, the attractions become virtually non-existent. So as a result, there appears to be a larger separation between the molecules, and as a result, electrical potential energy will increase. Their movements become really disorderly. There is no particular order, and as a result, the electrical potential energy begins to increase because this mean separation is increasing greatly. Then beyond 100 degrees Celsius, the molecules are really fast. Kinetic energy is really increasing. Maximum electrical potential energy would be gained because they are virtually non-relatable to each other, right? So that is actually what happens here. Then when water is heated, when there is a change of state, right, we have to continuously provide energy, and you know that there is no change in temperature, right? So that part, that energy is used to break free from one another, right? So their potential energy is increasing. In the meantime, right, the molecules will start moving faster because the kinetic energy is also increasing. The hardest point to appreciate is that you can put energy into the system without its temperature rising. This happens during any change of state. And so, we have studied this in O levels also. There is a period of time when we have to continuously supply energy, but there is no change in temperature. We have discussed about latent heat of fusion, etc. I hope you can remember them, right? So this energy is used to break the bonds between the neighboring molecules, right? And this latent means latent is hidden, and it is not something that is used to break up the bonds, but not to do something that is apparent, because that energy seems to disappear. Then at the same time, temperature is is defined as the average kinetic energy of the molecules. So when you put a thermometer into water molecules collide with the walls of the thermometer, and that actually results in the internal, whatever the contents, to alcohol or mercury, to increase its kinetic energy, right? When there is a change of state, right? When there is a change of state, no kinetic energy is change, because that the energy is used to break the bonds between them, right? So as a result, there is no change in temperature. Then in the above in that the first graph, section BC, that is melting ice, right? That part, and section DE, that is the boiling. In BC part, right? In this part, you can see that the energy content is much lesser than this. We need to figure out why, right? It takes lesser energy, because this happens because when a solid is melting, molecules are still bonded to most of their immediate neighbors, right? When a liquid is boiling, right, each molecule has to break free from its neighbors, right? Melting, right? Melting does not involve breaking a lot of bonds, because it is still, there are still some attachments. Boiling needs, that is it is almost all of them are broken away, right? So that is one thing that you need to understand. Then we come to evaporation. You know that evaporation is different from boiling, because evaporation can take place during a period of temperatures. It doesn't have to become a liquid to change into a gas, right? When a liquid changes to a gas without being boiled, we call that evaporation, right? All the, not only water that evaporates, all the even the other things without reaching the boiling point can evaporate, right? So if you so obviously you know that they have to start moving faster and gain that escape velocity, right? So whatever is able to move fast is what escapes, and that is what becomes part of the evaporation process, right? Now if you have how does it there are external factors that affect the rate of evaporation. Now for example, if you rub some alcohol onto your hand and if you blow at it, you will feel very cold, because that highly volatile liquid would evaporate, right? So this thing, evaporation is a very important part of cooling down objects. Our body, you know that we sweat, and that sweat is evaporated to make our body cool down. So those are examples for this. You have to remember that it happens because of fast moving particles, right? So the high energy, high average kinetic energy, there is some molecules will have higher kinetic energy than the others, right? So there is a net outflow of energetic molecules from the liquid, and that results in the leaving below average kinetic energy molecules in the liquid, right? So then what happens is, when you keep something to cool down, so now let's say something is kept, you keep a high boiling water, you boil some water, and then you switch off the switch off the stove or whatever the fireplace or something that you use to boil it, you switch it off and you leave it. Then after some time you will see that the temperature is also dropping. Why is that? The high energy molecules would escape, they would evaporate. But now the temperature is decreasing from 100, so still the vapor is going away. That is because the high average kinetic energy things will go away, and the low kinetic energy molecules will remain in it, and the temperature drops. I hope you understood. And if you have any questions, you can ask. If you do not have any questions, please do question number 2, and I will give you a note in the next video as well. But before you do the note, please try to do the question.